All right, so we're going to do the warm-up on the on the video today because it's kind of relevant to where we're going with this and kind of review what we did yesterday. So we got 2 points, -3, 4, and 5, -1, and it says to find the slope of the line that connects the 2 points. So we have to kind of remember that formula from Algebra 1. First of all, we use M for slope. What was the formula for slope if we have 2 points? Y sub 2 minus Y sub 1 over X sub 2 minus X sub 1. Yeah, and we called that yesterday, not the Sonic, not the Whataburger, but the Chick-fil-A, right. The DQ, which stands for, not Dairy Queen, but the difference quotient, right? So that's important that you remember that. That's the difference quotient. Now, it doesn't really matter which point you start with, but to develop good habits, you should always start with the point that has the larger X value, okay? So when we start looking at applications with time, then the change in Y ends up being the displacement if you do it that way. If not, it's the opposite of displacement. So we'll plug in the -1 first. So -1 minus 4 all over 5 minus -3. So there's your difference quotient plugged in, and now we evaluate it, and you get -5 over 8. So that is the slope of the line, which means in terms of rates of change, is this the average rate of change or the instantaneous rate of change? The way we calculated it as a difference quotient, in general, it's the average rate of change. So I abbreviate that ROC between the 2 points. But what do we know about the slope of a line anywhere and everywhere? It's the same. So this also ends up being the instantaneous rate of change at any point on the line. Okay, it's the average rate of change between any 2 points, not just the 2 points we used, but because it's a line, it's also the instantaneous rate of change at any point on the line. And the second one is the one that we talked about briefly yesterday. That's the one that can actually pose a problem when you don't have lines. Okay, and we'll kind of revisit that here today. All right, so now to write the equation of the line, you probably remember one equation of a line, right? If someone hits you hard on the back of the head, what might just come out involuntarily? Y equals M is supposed to be, right? It's like, whoa, where did that come from? Came from Algebra 1. You probably cannot force yourself to unmemorize that, huh? Right? It's ingrained in you. Y equals Mx plus B, Mx plus B. And of course, M is the what? Slope, and B, the y-intercept. Why do we call B the y-intercept? Why do we use B? Anyone know? We use M because it's the French or Spanish verb for to climb a mountain, right? But B for y-intercept, it's because A is used for the x-intercept. That's why. There's a form called intercept form, and A is the x-intercept, B is the y-intercept. So it's really kind of arbitrary, but the fact that X comes before Y in the alphabet song and A comes before B in the alphabet song, we use B for y-intercepts and A for x-intercepts. Okay, so if you're curious about that. Now think of this as a formula with how many unknowns, how many variables in it? 4, right? Y, M, X, and B. And so to use any formula, you have to know all but one. If you can know all but one, you can plug in and solve for the missing one. That's called algebra. Well, that means I need to know 3 of these 4. Do I know 3 of the 4? Yes, okay. I need a point x, y. To write an equation of a line, I need a point. Do I have at least 1 point? Yeah, I actually got 2 points. So it doesn't matter which one we use. What would y'all prefer? 5, -1? Okay, I'll go with it. And then we need M, which is the slope. Do we have the slope? We just found it, right? We just found it to be -5/8. So we can plug in to that formula and solve for the missing value B. So here we go. If we plug in, we get -1 equals -5/8 times X, which is 5, plus B. And now to solve for B, we'll just kind of combine this to get -25/8. And now you have 2 options. You can either multiply everything through by 8 and eradicate the fraction, or embrace the fractions. What do y'all want to do? Embrace the fractions? Good answer. All right. Yeah. Face your fears and they go away. So if I add that to the other side, or they eat you, right? Either way, you don't have to worry about your fears anymore. So 25/8 minus 1, that's the same as 25 minus 8/8. 25 minus 8 is 17. So we get 17/8 equals B. Now we found B, but what we were really after was the equation of the line. We wanted y in terms of x. And so in this formula up here, what we really wanted were m and b, so we could just drop them in and get the equation. So now we have to write the equation. So when you come up with your final answer and you want to make some kind of transition, you could say therefore or thus. No thanks. I like to use so. Y equals m, which we just found, negative 5/8, times x plus 17/8. There you go. There's the equation in slope-intercept form. Beautiful. So that was a two-step process. So we really only need 2 points to find the equation of a line, but ultimately it was nicer to have a point and a slope. So in calculus, we write equations of lines almost on a daily basis. And every time we do, I say, what do we need for the equation of a line? And they all go, point and a slope. And I go, yes, or, and they all say, slope and a point, right? Either way. So what do we need for the equation of a line? Slope and a point, or point and a slope. Either one. It doesn't matter which one. You just have to have one of those two. Okay, so that was a lot of work, though, right? It was like, plug in, solve for B, and then plug it back in. Right? You're away from your phone too long if you do it that way, right? Is there a faster, shorter, quicker way so that you can get to your notifications faster? Y'all are interested in more efficiencies so that you don't have to be away from your phone for as long, and I have a method for that, okay? Let's look at this equation right here. M equals, again, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. What do we call that? Difference quotient. It gives you the average rate of change between those 2 points. Okay. On a curve, it also gives you the slope of the what line? We talked about that yesterday. No, not the tangent line, the secant line. The slope of the secant line is the one that connects a curve in 2 points. On a line is its own secant line. Okay, now do something for me. Get rid of the little subscripts of 2's. Just call it y minus y sub 1 over x minus x sub 1. It's the same thing, we're just labeling them differently. If I just multiply both sides by the denominator, I get y minus y sub 1 equals m times x minus x sub 1. This is another form of a line called the point slope formula. Because for this, all you need is the point, x sub 1, y sub 1, and the slope. Drop it in, and you have your equation. It comes from the difference quotient. Now, when we sketch lines, we like to solve them for what variable? The other one. Y. We like to solve them for y, right? Your calculator actually has a y equals button. So if we solve this one for y, by adding y sub 1 to both sides, we get y sub 1 plus m times x minus x sub 1. And this one right here is the only form of the equation of a line that you're going to ever need ever again in your entire life if you're interested in writing the equation of a line. It's the only one you're going to need, okay? You need a point and a slope. This one is called Taylor form. Taylor form. It's solved for y. It's the y value plus the slope times x minus the x value. It's in this form because Brooke Taylor, the English mathematician, came up with a way to determine a polynomial of nth degree to model some other transcendental function. So this is a first degree Taylor polynomial, but you just need to know that it's the equation of a line. So let's go ahead and find the equation this way. It'll be less work. So y equals, what was our y value? It was negative 1, plus the slope, which is really now minus 5/8, times x minus the x value of 5. Done. There's the equation of a line. I didn't have to do a two-step process of plug in, solve for b, and then plug back in. I just drop it in and walk away. That's the equation of a line. Beautiful. Now, if you wanted it to be in a different form, like slope-intercept form, once you create the equation, you can algebraically manipulate it. So let's just verify that that is, in fact, the same as that. We just have to distribute. So if we do that, we get y equals negative 1 minus 5/8x, and this becomes plus 25/8. And now if we write it in descending order, negative 5/8x, 25/8 minus 1 is 17/8. And it's the same. So wow. What's the only form of the equation of a line you're ever going to need ever again to write an equation of a line if you have the point and the slope? What's it called? Taylor form. Yeah, Taylor form. You should memorize it. Memorize Taylor form. Y equals, and then the y value plus the slope times x minus the x value. Sweet. We will study Taylor polynomials of higher degree if you go on to take BC calculus. Hello. Thank you. Dane is, okay. He is actually not in my class. I think he's probably in an AP exam maybe this morning. Oh, okay. Yeah. AP Lits this morning. Okay. Is he AP Litting? Yeah, okay. Okay, so there you go. That's a pretty good warm-up. Y'all warm? I'm warm. I'm actually overheated a little bit. For the warm-up, you're right, good. So let's move back to the notes then. All right, so yeah, here's slope of a line, slope of a line, slope of a line. Just to kind of summarize. The slope of the line in the form y equals mx plus b has a constant slope of m at any point and at all points, okay? So for a line, it's not only the average rate of change between any 2 points, but it's also the instantaneous rate of change at every point. Now, there are two types of slopes that are very, very important. So let's kind of come back up here to the warm-up. Let's look at a horizontal line. A horizontal line looks like this, right? That's a horizontal line. Now you put arrows on the end. What's the slope of a horizontal line? 0, right? When you learn to ski, you learn to ski on a 0 slope because it's not called skiing, it's called walking, right? You have to learn to walk before you can ski, right? Now, why is it a slope of 0? Is it because the word 0 has horizontal line segments in the Z? Is that why? Oh, I doubt it, but that's a good way to help me remember. Thank you. No, why is it 0? Let's pick some arbitrary points. Let's say that we're on the number line or the y-axis somewhere. Let's say that this is like -3, 4. There's no rise. Good. Let's call this 5. What would the y value have to be? 4. On a horizontal line, the y values are all the same. The x values vary. So if you found the slope, you would have 4 minus 4 all over 5 minus -3, which would give you 0 over 8. What's 0 divided by any non-zero number? 0. Because there's no rise, the y's difference is 0. So anytime you get 0 over non-zero, you're going to get 0. And that's why a horizontal line has a slope of 0. All right. What do you think the other special type of line is? Straight line. Someone said last period. Nice. Now, how about a vertical line? Let's draw a vertical line. There it is. What's the slope of a vertical line? Yeah, the slope m. Oops, that's an ugly m. The slope is undefined. Now, that's a very rudimentary definition of the slope. Undefined, okay? You could also say that it has no slope. That's another rudimentary way to say it. It doesn't exist. And the N in no has vertical lines, if that helps you. But what I want y'all to learn now is a vertical line has undefined slope because it is plus or minus infinity. All right? It's plus or minus infinity. Can you ski down a vertical slope? No. It's called what? Falling, okay? So you can't ski down it. It has no slope because it's infinite. So let's look at some arbitrary points on here. This one might be the point -2, 5, and this one might be -2, -1, right? Those would be 2 points. The x values would now be the same. So if you computed the slope, it'd be the change in the y values, 5 minus -1, all over -2 minus -2. So in this case, we end up with 6 over 0. And what's non-zero divided by 0? It's undefined, right? But it's undefined because there's some kind of what? Infinity, right. So remember, non-zero over 0 always meant vertical asymptote on the graph, right? And a vertical asymptote is the thing that forces your y values to what? Either to infinity or negative infinity. So non-zero over 0 is plus or minus infinity. So in that essence, if 0 over non-zero and non-zero over 0 are reciprocals of each other, How are 0 and infinity related? They're reciprocals, yeah. What's the reciprocal of 0? Infinity. What's the reciprocal of infinity? 0. Yeah, remember that. That's pretty cool. Now, whether it's positive infinity or negative infinity, you have to kind of look next door. So, like, if you have the graph of the cube root of x, it looks like that. Back in the day when I was a skater, we always talked about, man, how much vert does that ramp have, dude, right? Does it go vert, right? So here would be the cube root of x, and it goes vert right there. Because it goes vert, what is the tangent line there? Well, it would be a vertical line. So right there, the slope at that vertical tangent line where it goes vert would be plus or minus infinity. What do you think? It would be plus infinity because that function is increasing, strictly or monotonically increasing through it. Whereas if you look at the graph of negative x cubed, that goes vertical right there, what's the slope at that point? It's monotonic decreasing, so when it goes vertical there, the slope is negative infinity. So you have to look at context clues to decide if the slope is plus or minus infinity. If you're just looking at a vertical line, it's hard to know if the slope of that vertical line that stands by itself is plus or minus infinity, right? It depends if you're falling down, that would be negative infinity, or if you're falling up, that would be positive infinity. Falling up. Yep, I see it. At least once a day at the top of the stairwells. Some people fall up the last 2 steps. It's kind of cool. Defying gravity. I should play that in between classes. What? Yeah, oh yeah, oh, all the time. As the day goes on, it's a lot easier to trip up those last stairs. People get lazier or it's just they're tired, and then they don't pick their feet up all the way, and they hit the riser, and they fall up. Yeah, and then they look around, and they dust themselves off, and, you know, that never happened. Some people go with it. Okay. All right, so let's take a look at example 3. We kind of alluded to this yesterday. Let's look at the graph of x squared plus 1. X squared plus 1 is our old friend x squared plus 1. It has a y-intercept of 1, and he's smiling because he's in a math class, right? There we go. It's a parabola that opens up. First of all, what's the slope of this graph? Can we find it? Is it a single value like it is for a line? No. A line changes at a constant rate. Does this function change at a constant rate? No. It actually decreases and then increases, so there's no way it could change at a constant rate. Now, it decreases at a variable rate and increases at a variable rate. So there's no way the slope could be a constant, okay? But I can ask this question, where are the slopes negative? I'll just say less than 0. Where are the slopes less than 0? Yeah, good. We usually list it in terms of x. We don't just say to the left of the y-axis. We'll just say when x is less than 0. Everywhere to the left of the y-axis, the graph is decreasing, so the slopes are negative. Where are the slopes positive, greater than 0? To the right of 0? Yeah, when x is greater than 0, the slopes are positive. Now, are they the same positive or the same negative value? No. If you look at a slope at a point, let's just arbitrarily look at this. I'll get rid of this here in a second. What does it mean to talk about the slope at a single point? We mentioned that yesterday. It comes down to me trying to find the slope of the what line? The tangent line. Okay, there's the tangent line. If I can find the slope of the tangent line at that single point, I'll have the slope of that graph at that point. I will have its instantaneous rate of change, okay? And notice that, first of all, if I were to grab this line, I can kind of move it. So as I surf the curve, look what's happening. These are tangent lines. As I move from left to right, my tangent lines are all different, aren't they, right? I'll start it back again over here. I have a small tangent line, and as I move to the right, ooh, this is not working. I'm like surfing the curve from underneath. My tangent lines are getting steeper and steeper. You see that? So the slopes vary all over the place. There's not a single slope like there is for a line. But if I can find the slope of that tangent line, I'll have the slope at that point. That's what this whole section is going to kind of get to. So we're not going to do that yet. All right, so now, where, if anywhere, is the slope equal to 0? Is the slope ever equal to 0? That is, does the tangent line ever appear to be horizontal? Where? At the point 0, 1, right? When x is what? When x is 0. At the vertex, we appear to have a horizontal tangent line. And so right there, the slope is actually 0. Those are easy to spot. You don't really need to do any calculations to determine a horizontal tangent line, because wherever the graph does a vertical about face, what goes up, what must come down, right? So if the instantaneous rate of change of position is known as velocity, what goes up must come down. You're going to have a horizontal tangent at the top, and that's where the rate of change of position must be equal to the slope of the line, which is 0. And what do we call the instantaneous rate of change of position? If we describe how positions change in feet per second, we're talking about velocity. What's the velocity of an object at the very top if you throw it up right before it turns around and comes back down? It's 0. Yeah. So that's the Newtonian perspective. The instantaneous rate of change of position is velocity. That's what Newton was interested in finding. What is the instantaneous velocity? Leibniz was interested in finding the slope of the line. Okay, so there you go. Let's take a look then at a specific point. Let's just call it -3, right here, -3. I am actually interested in the actual value of that slope. Oops, let me try that one more time. I want the actual value of that slope at that single point. Okay, so the y value there is actually what? When you plug in a -3, you square it, you get 9 plus 1 is 10. So at the point -3/10, I want to know what the value, the quantitative value of that slope is. Can anyone give it to me just by looking at it? I only can tell that it's what sign? Negative. That's all I know. That's all I know. If I look to the point immediately to the left, I know the line is going to be steeper. And if I look immediately to the right, I know it's going to be less steep. So I can compare it relatively to what's around it, but I can't find its actual value. In order to find the actual value of a slope, I need how many points? 2. So if I chose another point on the line, I would be guessing, right? I have no idea what another point on the line is, so that would kind of lose its accuracy. So the best thing I could do is to choose another point on the parabola where I know the ordered pair. All right, so that's what we're going to do here in a second on example 4. Okay? So let's jump down here and just kind of summarize. First of all, calculating slopes between 2 points is easy. You just calculate the what? The difference quotient. That's the change in y over the change in x. Okay. If you use algebra, you can compute the average rate of change using the difference quotient, which gives you the slope of the secant line. Okay? It's interesting that average rate of change, that would be kind of a Newtonian perspective. And the secant line, that would be a Leibnizian perspective. Leibnizian perspective. But that doesn't require calculus at all. That's algebra, right? The calculus kicks in when we try to find not the slope of the secant line, but the slope of the tangent line. And that would again be the Leibnizian perspective. And the Newtonian perspective says that that is also the instantaneous rate of change. So Leibniz and Newton were discovering calculus at roughly the same time in different parts of the world, motivated by very, very different things. Newton, again, was looking at the stars, trying to determine how fast the planets were moving in their orbits. That was motion. And Leibniz was just looking at a graph, saying, what's the slope of the tangent line? They used completely different notation, motivated by very different things. They called their method something very, very different. Y'all remember what I said Newton over here called his? The method of not change, but what's another word for things that change? Things fluctuate. So he called his the method of fluxions, for fluctuations. And Leibniz called his the method of infinitely small things we call infinitesimals, right? If something is infinitely small, We say it's infinitesimally small. So he called his the method of infinitesimals, Leibniz did, and Newton called his the method of fluxions. It turns out that they were actually trying to answer the exact same question, motivated by different things, seemingly unrelated, right? How fast is that thing moving at that moment in time? What's the slope of that tangent line? They answer the exact same question. So, interesting fact, if you want to read this, I'll read it with you. Calculus was discovered independently by two different dudes in two different parts of the world at roughly the same time. 1674, Leibniz was in Germany trying to find the slope of the tangent line, while in 1666, just a smidgen earlier, right? A smidgen earlier, 8 years earlier, Isaac Newton was in England trying to determine the instantaneous rate of change of the planets. But it turns out that the solution to both of their questions was differential calculus, to be specific. Okay, so if you look at the dates there, who actually, according to this, discovered calculus first? Isaac Newton. But there was a priority dispute that evolved between the two, and an ugly feud. Because in academic worlds, it is not necessarily who discovers something first that gets credit. It's the person who first publishes the work. It's all about publishing. If you publish an idea first, you're going to get credit for it. So Newton discovered his in 1666, but Newton was good at everything. So first of all, he wasn't interested necessarily in publishing because he was like, oh, I figured out how fast the planets are moving. Okay, what next? Let's work with optics. Okay, got that figured out. Gravity, got it. Let's try to spin yarn into gold. Didn't happen for him. Okay, so first of all, he didn't publish for that reason, but he had also tried to publish previously, and the intellectual society shot him down. They saw him as a threat, and so they tried to discredit him. The British Royal Society, those are the guys that wore the big wigs, and they were in charge of all the intellectual property at that time during the world. They tried to discredit Newton, so he was kind of gun shy after that. He didn't want to publish, so he didn't publish. But then 1674, Leibniz comes up with his version, infinitesimals, and he publishes, and it sweeps the nation. And then Newton catches wind of it, and he realizes what it is, and he's like, hey, wait a minute. I did that first. I just didn't publish, right? And so he actually accused Leibniz of stealing his work. He actually claimed that his work got out, and Leibniz caught wind of it and read it and tried to treat it as his own, which was absurd, right? Because they were motivated by different things. They had completely different notations, called it different things. So it was an absurd allegation. But after that, Newton got real serious. Edmund Halley kind of came by, convinced him to publish, and then Newton got more and more confident, and eventually himself became head of the Royal Society. He's now the main guy in charge of controlling all the intellectual property of the day. And what are you going to do when you're in charge? What are you going to do to your bitter rival who's trying to, quote, steal your work? Yeah, you're going to discredit him, and you're going to make sure that he's not even a footnote in history. So that's why a lot of people haven't heard of Leibniz. Newton gets all the credit, right? But Leibniz did, in fact, nowadays we typically give them both credit, and it's just remarkable that roughly the same time, the world was ready for calculus, and they both discovered it completely independently of each other. So anyway, pretty neat stuff. So important ideas. Average rate of change is the slope of the secant line. Average rate, one last caveat to that story I'll mention. Yeah, we should probably say that real quickly here. The Leibniz can say that he does get the last laugh, all right? Because while Newton tended to get credit, Newton's method had really, really arcane notation, and we don't use Newton's notation of fluxions anymore. And Newton actually divided by zero in his calculations, which no one could explain how he did it. They just kind of turned a blind eye to it. So Leibniz, on the other hand, never divided by zero, and his notation was so superior, we still use Leibniz notation today. The dx you see on the poster and this little super S called the integral, those are Leibniz notation. So we use Leibniz notation. It's kind of like a daily way to honor Leibniz in the way we practice calculus. So anyway, so important ideas. Average rate of change, that is algebra. It's the slope of the secant line. That was the old machinery. Still kind of works, but maybe not as useful as the power of the next thing that was a-coming, which was finding the instantaneous rate of change, which is the exact same thing as finding the slope of the tangent line, and that is calculus, right? Calculus. So the question is now, how'd they do it? How'd they do it? You saw the magic trick. Now you want to know, how was it done? How did they find the slope of a tangent line that required 2 points if they only had 1 point? How do you find the slope of a line with only 1 point if you need 2 points? How did they do it? What's that? It's magic. So what we're going to do here on example 4 is not a hint necessarily of how our mathematical forefathers got around that problem of having only 1 point, but maybe I could say here's the aroma or a whiff, right? Here's the aroma. We're not even going to taste it. We're just going to like maybe smell it a little bit. I see what we're getting at. So let's say, okay, I want to find the slope of that graph, x squared plus 1, at x equals negative 3. I want to find the slope of the tangent line. I want to find the instantaneous rate of change of that graph at that point. Well, because the math requires 2 points, we're going to have to give in and use the second point. So let's go ahead and find the average rate of change, or the slope of the secant line, between the two x values, negative 3 and 5. All right? So let's see what that's going to look like. If I have to choose another value, I'll call it 5. We'll use purple. 5 is going to be somewhere way over here. It's going to be way up there. If I then find the slope of that line, that's called the what line? Secant line. Now, is that secant line going to be a good approximation of the tangent line? Not even. Really, really bad approximation, right? One of them is increasing, the secant line is increasing, positive slope, and the tangent line is decreasing. But we can find the slope of that line. So let's go ahead and do it. We'll label this as average ROC, which is short for average rock, as someone last period so eloquently said. AVG ROC is average rate of change. And because it's function notation, we're going to say f of 5 minus f of negative 3, all over 5 minus negative 3. So again, you want to get in the habit of using the larger x value first. When you do that, the numerator, when you start looking at applications of Newtonian applications of motion, the numerator becomes the displacement, which is an interesting quantity in and of itself. All right, so if we plug in, we get 5 squared is 25 plus 1, that's 26, minus f of negative 3, you already found is 10, all over 8. So that becomes 16 over 8, which is 2. So that is the slope of the secant line. That's also the average rate of change. They're the exact same thing. All right, so if you look at that geometrically, that means to get from negative x equals negative 3 to 5, on average, we go up 2 over 1, 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 up 2 over 1. It's kind of like a shortcut, right? Cutting across the field to get there. That's not how we actually got there, though, right? We got there by going down and then up at variable rates, okay? All right, so if the idea is we have to use a second point and we want the secant line to become an approximation of the tangent line, picking a value that's 8 units away, like at 5, kind of not of a good idea, right? So let's choose another point that's closer to negative 3. Let's use negative 3 and 2. So let's see what that guy would look like. Let's come up here and draw it first. If I choose, what did I say, 2? 2 is going to be right around here. And now if I draw that line, that's another secant line. That would be a better approximation of the red tangent line, wouldn't it? At least now they're both negative slopes. But we can find that by using the difference quotient. So average rate of change, or slope of the secant line, it's f of 2 minus f of negative 3, all over 2 minus negative 3. So what is f of 2? You plug it into your function f of x equals x squared plus 1, and you get 5. Minus f of negative 3 is always going to be 10, so minus 10 all over 2 plus 3 is 5. So you end up with negative 5/5, which is negative 1. So now at least it's a negative slope. We knew the tangent line was negative. So again, that is not only the slope of that green line, but it means to get from negative 3 to 2, on average we go down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. Where in actuality, we went all the way down and then came back up. See that? All right, so can we get a better approximation than the green line for the red line? And the answer is yeah. Let's choose a point that's even closer to negative 3 than 2. Let's try 0. right? So let's go ahead, let me pick a flavor for that. Let's use pink. So if I come up here, well, not pink, let's use brown. So there's 0, right? So now if I draw that secant line, that's going to look like this. I got to move it. Okay. There we go, something like that. That brown line is now going to be a better approximation of the red line than the green one was, yes? You see how it's getting a little bit closer? So let's go ahead and compute that. Using the difference quotient, the average rate of change. Right here, the average rate of change is going to equal f of 0 minus f of negative 3 all over 0 minus negative 3. What do we call that? Difference quotient. Okay, good. So f of 0 is 0 squared plus 1, which is 1, minus f of 3 is still going to be 10, all over 3. So it gives you negative 9/3, which is negative 3. So negative 3 is not only the slope of that brown secant line, but now you can say, maybe the tangent line is about negative 3-ish, right? It's actually going to be a little bit steeper, so maybe it's negative 3.5, maybe it's negative 4. The idea is now we can start using the secant line as an approximation for the red line. But can we do better than that? Yes. Let's choose a point that's even closer to negative 3, like negative 2. That one's only 1 unit away. So I will use purple. Have I already used purple? Yeah, let's use burnt orange. Yeah. All right, so negative 2 is going to be right around here. Yeah, UT. If I find the slope of that one's going to be now right in here somewhere. Now, I'm kind of losing my ability to draw more lines in there, but if you notice, the orange line and the red line are getting closer to each other's slope, right? The orange line that I just drew is a better approximation than the brown line that I drew. So let's go ahead and figure out what the slope of that burnt orange line is using the average rate of change. So here we go. The average rate of change, ROC, is f of negative 2 minus f of negative 3 all over negative 2 minus negative 3. So f of negative 2, when you plug it in, is 4 plus 1 is 5. Minus, that's still 10, all over 1. So you get negative 5 over 1, which is negative 5. So if the slope of the orange line is negative 5, now we could say that the tangent line, what we're really interested, could be approximately negative 5, yeah? We actually know it's a little bit steeper than that, so we can maybe say it's maybe closer to negative 6 or negative 5.5. Now, you can see what I'm doing here. I'm anchoring my negative 3, but that second point that I'm required to use, what have I been doing with it the whole time? Moving it closer and closer and closer and closer to the point I'm interested in, negative 3. And as long as I continue to do that, but keep it as 2 distinct points, I can continue to use the algebra slope, the difference quotient, the change in the two y values over the change in the two x values. And as I do that, the secant line is going to become a better and better approximation of the tangent line. So let's go ahead and say this. As x approaches negative 3, we write that mathematically like this. As the other x value that I have to use, that's what I'm calling x, the other x value that I have to use. As it approaches negative 3, comma, the secant slopes approach the tangent slope. So that's a hugely important idea. As that second point that I'm required to use gets closer and closer and closer to negative 3, the point I'm interested in, the secant slopes that I'm calculating approach the tangent slopes, which means, I should add this in here too, that from the Newtonian perspective, the average rate of changes approach the instantaneous rate of change. So the top one would be Leibniz and the bottom would be Newton, okay? It's the same thing. So here's kind of the aroma of where the magic comes in. Ready? How close then can I make that second point to -3 without actually making it -3? How close can I make those 2 points but still have them be distinct? Infinitely close, right? I can move that second point infinitely close to -3. I'm going to start losing my ability to show it as a different point and for sure drawing secant lines. But in theory, it can move infinitely close to -3 without actually getting there. What would that space be between those two then? Infinitely small, which we call what? If it's infinitely small, we call it infinitesimally small. And that's what Leibniz was working with. He was saying if you can let those 2 points be infinitesimally close to each other, essentially then, when they are infinitesimally close to each other, these two things right here not only begin to approximate each other, but they begin to become and equal each other. Yes. Do you see a limiting value in there? Remember we talked about the limit earlier in the year? The limit is that notion of motion of getting closer and closer to something without getting there. The limit is in here, okay? As we get infinitely close to the point of interest, the secant slopes actually equal the tangent slopes, and the average rates of change actually start equaling the instantaneous rate of change. Now, Galileo, when he did his rolling balls down inclined planes, he was doing these calculations already before Newton and Leibniz. He was computing average rates of changes of position over very small time intervals to try to approximate instantaneous velocity. But he was doing tedious calculations. The magic comes in what Leibniz and Newton did, where they kind of did it with variables and made a theoretical leap into a formula that is actually super easy to find. And then once you have that formula, it's just plug it in and evaluate. Pretty cool stuff. So we'll stop right there for today. And I hope that you are getting intrigued, if nothing else. So remember, the worksheet awaits, and you can do your algebra